Welcome to this lecture on fundamentals of biomolecules. Today, we're diving into the fascinating world of enzyme inhibition. Enzymes are the biological machines that keep us alive, but sometimes they need to be slowed down or stopped entirely. Understanding how this happens is the key to modern medicine, pharmacology, and toxicology. Let us begin our journey. To understand our first major concept, competitive inhibition, imagine you have a specific key that fits perfectly into a padlock. Now, imagine someone creates a fake key with the exact same shape, but without the right grooves. If you stick this fake key into the lock, it gets stuck, and the real key cannot enter. This is exactly how competitive inhibition works in our bodies. A molecule structurally similar to the normal substrate binds directly to the active site of an enzyme. Because they have similar shapes, the inhibitor and the substrate actively compete for the exact same physical space. Now that we understand what competitive inhibition is, let us look at its most defining characteristic. When the inhibitor is bound, it forms an inactive complex. However, if you have a million real keys and only one fake key, the fake key rarely wins. By adding a massive amount of substrate, it completely outcompetes the inhibitor. This means the maximum possible speed of the reaction remains completely unchanged. This concept is incredibly important in modern medicine. For example, statin drugs lower human cholesterol by competitively inhibiting the enzyme responsible for synthesizing it. This allows doctors to safely fine-tune biochemical pathways without permanently destroying the patient's enzymes. Before we can see how the reaction speed changes, we first need to define how strongly the inhibitor affects the enzyme mathematically. We do this by calculating a modification factor, represented by the Greek letter alpha. This formula comes from the ratio of the inhibitor concentration to its binding strength. The symbol I in brackets represents the concentration of the inhibitor present in the system. The symbol Ki represents the inhibition constant, which measures how tightly the inhibitor binds to the enzyme. A smaller Ki means the inhibitor binds very tightly, making it a stronger inhibitor. As the inhibitor concentration increases, the value of alpha also increases, indicating a stronger inhibitory effect. Now that we have our modification factor, we can apply it to the standard Michaelis-Menten equation to see how the reaction speed changes. Conceptually, this formula shows us the initial velocity of the enzyme-catalyzed reaction when a competitive inhibitor is present. The symbol V0 represents this initial velocity. Vmax represents the maximum possible velocity when the enzyme is fully saturated. S, in brackets, stands for the substrate concentration. Finally, Km is the Michaelis constant, indicating the substrate concentration needed to reach half of the maximum velocity. Notice that the modification factor alpha is multiplied only by Km. This mathematically proves that the apparent Michaelis constant increases, while the maximum velocity remains completely unaffected. Let us see this formula in action with a concrete example. A laboratory researcher is studying an enzyme with a normal Michaelis constant of 5 millimolar. They introduce a competitive inhibitor at a concentration of 8 millimolar with an inhibition constant of 2 millimolar. We need to find the new apparent Michaelis constant. First, we calculate the modification factor by dividing the inhibitor concentration of 8 by the inhibition constant of 2, which gives 4. Adding 1 gives us a modification factor of 5. We then multiply this factor of 5 by the original Michaelis constant of 5 millimolar. The final answer is 25 millimolar.
Physically, this means the enzyme now requires 5 times as much substrate to reach half of its maximum velocity.
Building on the previous scenario, let us calculate the initial velocity. We are given a maximum velocity of 100 micromoles per minute. The apparent Michaelis constant is now 25 millimolar, and the researcher sets the substrate concentration to 25 millimolar as well. We plug these values into our modified Michaelis-Menten equation. In the numerator, we multiply 100 by 25 to get 2,500. In the denominator, we add 25 and 25 to get 50. Dividing 2,500 by 50 gives us a final initial velocity of 50 micromoles per minute. Because the substrate concentration exactly matches the new apparent Michaelis constant, the reaction proceeds at exactly half of its maximum velocity, proving the fundamental relationship holds true. To visualize what we just calculated, let us look at the Lineweaver-Burke plot for competitive inhibition. This is a double reciprocal graph. The horizontal axis represents 1 over the substrate concentration, and the vertical axis represents 1 over the initial velocity. Notice the two lines, the uninhibited enzyme and the competitively inhibited enzyme. They intersect at the exact same point on the vertical axis. This visualizes our earlier point that the maximum velocity remains completely unchanged. However, look at where they cross the horizontal axis. The inhibited line crosses closer to 0. Because this axis represents -1 over the Michaelis constant, this shift to the right perfectly illustrates that the apparent Michaelis constant has increased, meaning the enzyme appears less efficient. Now that we have mastered competitive inhibition, let us move to our second major concept, non-competitive inhibition. Imagine a vending machine that dispenses snacks when you insert a coin. The coin slot is the active site. Now, imagine someone unplugs the power cord at the back. You can insert as many coins as you want, but the machine will never dispense a snack. Flooding the machine with coins does absolutely nothing. This is exactly how non-competitive inhibition works. The inhibitor binds to a completely different location on the enzyme, known as an allosteric site. It does not physically block the substrate. Instead, it changes the overall three-dimensional shape of the enzyme, breaking its catalytic machinery so it cannot convert substrate into product. This mechanism of breaking the enzyme's machinery is crucial for understanding both natural cellular regulation and dangerous toxicological effects. In nature, cells use non-competitive inhibitors to temporarily turn off metabolic pathways when they have produced enough of a specific product. It is a natural feedback loop. However, in toxicology, heavy metals like lead and mercury act as severe non-competitive inhibitors. They bind to critical enzymes in the nervous system and shut them down. Because adding more substrate does not help overcome this blockade, these poisons are incredibly dangerous and difficult to treat. Understanding this mechanism allows scientists to develop specific antidotes that target and remove the inhibitor from the allosteric site, restoring the enzyme's function. To model this non-competitive behavior mathematically, we must show that the enzyme's maximum speed is permanently reduced. We do this by dividing the original maximum velocity by the modification factor. In this formula, V prime max represents the new apparent maximum velocity of the enzyme in the presence of the inhibitor. V max is the original maximum velocity of the uninhibited enzyme. The symbol alpha is the same modification factor we used before, which depends on the inhibitor concentration. Because the original maximum velocity is divided by a factor greater than 1, the apparent maximum velocity is always lower than the original.
This mathematically proves that the enzyme can never reach its full original speed, no matter how much substrate is added.
Now, we substitute this new apparent maximum velocity into the Michaelis-Menten equation. This will show us how the overall reaction speed behaves under non-competitive inhibition. Here, V0 represents the initial velocity of the reaction. V prime max is the reduced apparent maximum velocity we just calculated. S, in brackets, represents the concentration of the substrate. Finally, Km is the original Michaelis constant. Notice that in pure non-competitive inhibition, the Michaelis constant remains completely unchanged. This equation shows that the reaction still follows normal Michaelis-Menten kinetics, but it operates under a permanently lowered speed limit. The fundamental binding affinity of the functional enzymes is the same. There are just fewer functional enzymes available to do the work. Let us apply this to a practical example. A biochemist is studying an enzyme that normally processes a substrate with a maximum velocity of 120 micromoles per second. They add a non-competitive inhibitor, and the modification factor is calculated to be 3. We need to determine the new apparent maximum velocity. We take the original maximum velocity of 120 and divide it by the modification factor of 3. This simple division gives us a final result of 40 micromoles per second. Physically, this means that even if we flood the test tube with an infinite amount of substrate, the enzyme can never work faster than this new limit of 40. The inhibitor has effectively taken 2/3 of the enzyme molecules completely offline. Using the same enzyme from our previous example, let us calculate the initial velocity at a specific substrate concentration. The new apparent maximum velocity is 40 micromoles per second. The enzyme has a Michaelis constant of 10 millimolar, which remains unchanged. The biochemist sets the substrate concentration to 10 millimolar. We plug these values into our equation. In the numerator, we multiply the apparent maximum velocity of 40 by the substrate concentration of 10, giving us 400. In the denominator, we add the Michaelis constant of 10 to the substrate concentration of 10, giving us 20. Dividing 400 by 20 yields a final initial velocity of 20 micromoles per second. Because the substrate concentration equals the Michaelis constant, the reaction runs at exactly half of its new lowered maximum velocity. Let us visualize this permanent speed reduction on a Lineweaver-Burke plot. Again, we have the uninhibited enzyme line and the inhibited enzyme line. This time, look at where they intersect. They meet at the exact same point on the horizontal axis. Because this axis represents the Michaelis constant, this proves visually that the binding affinity remains completely unchanged. The substrate can still bind perfectly well. However, look at the vertical axis, which represents 1 over the maximum velocity. The inhibited line crosses much higher up on the axis. Because this is a reciprocal plot, a higher intercept means a lower actual value. This upward shift perfectly illustrates the permanent decrease in the maximum velocity of the enzyme population caused by the broken catalytic machinery. We have covered a lot of ground today, so let us summarize the most important ideas. First, competitive inhibitors bind to the active site, fighting the substrate for space. They increase the apparent Michaelis constant, making the enzyme look less efficient. But they can be completely overcome by adding more substrate, leaving the maximum velocity unchanged. Second, non-competitive inhibitors bind to an allosteric site, breaking the enzyme's machinery without blocking the active site. They leave the Michaelis constant unchanged,
but cause a permanent decrease in the maximum velocity that no amount of substrate can fix. Understanding these two distinct mechanisms gives us the power to design life-saving drugs and treat dangerous poisonings. You now have a solid foundation in enzyme inhibition.